Hello mathematicians, thank you for joining me today. What we're going to do is look at the set nz, where n is an integer. Then nz is going to be the set of all multiples of n. That is, everything that can be written in the form of n times k such that k is an integer. If we take this set, what we want to do is show that it's a subgroup of the set of integers under addition. So what that means is that we have to show it's a subset of the set of integers, and that it itself, again, is a group. So now in order to show h is a subgroup, we had to show that it's a subset and itself a group. So in order to show it's a group, generally what you'd have to do is show that h together with the operation in g is again an operation on h, and then we get that it's going to be an associative operation, and we're going to get that we have identities and we have inverses. And so what we'll notice though is that, well, because we already know that g is a group, we already know that that operation is an operation on g, and we know that it is an associative operation, and that there's an identity in g, and that there are inverses in g. So a lot of the work that we would have to do is just repetition of the stuff that we would do for g using a smaller subset h of g. So instead of having to go through that whole process, what we can do instead is show that, well, if we can show that for any a and b and h, that a, b inverse is again in h, where we know h is a subset and it's a non-empty subset, then this is sufficient to show that h is a subgroup of g. So instead of walking through all of those steps, we're just going to show, well, h is a non-empty subset of g, and then we're going to show that for any a and b in h, a, b inverse, again, has to be in h. First thing we need to show is that nz is a non-empty subset of z. So what that means is that any element in nz is again going to be in z, and that there exists something in there. So I'm going to start off and say, well, let's suppose that a is in nz. Then I want to show that a has to be an integer. Well, we know that n is an integer, and we know that because a is in nz, by definition, a is equal to n times k for some integer k. But now, because n is an integer and k is an integer, then two integers multiplied together is again an integer, so we get that a has to be an integer. Therefore, nz has to be a subset of the set of integers. Now the only thing left to check is that it's not empty. So what I'm going to say is just, well, let's pick some element and let's say 0. Notice that 0 is any integer times 0, so therefore 0 is n times 0 for any integer. Hence, 0 is an nz. So we get that nz is indeed a non-empty subset of z. Alright, so now we have to do the work of our proof is, let's say that a and b are both in nz, then we have to show that, well, we had used the multiplication notation before, that is ab inverse is nz, but because we're working with addition here, I'm going to say that, well, we have to show that a plus the inverse of b is negative b, so a plus negative b is again in nz. So the goal is to take two arbitrary elements here and show a plus negative b is again in nz. So how would I do that? Well, I just kind of want to work my way around and say, okay, what does this mean, and somehow can we get this out? The first thing I'm going to work with is the definition of nz, and that means that a is a multiple of n, and b is a multiple of n. So I'm going to say a is n times some integer k1, and b is n times some integer k2. So I get a is nk1, b is nk2 for k1 and k2 integers. Now, if I want to show that a plus b is in nz, I have to show that a plus negative b is a multiple of n. So what we have to show is that a plus negative b is equal to n times, let's say, k3, because I've already used k1 and k2, for k3 an integer. So notice I'm working my way from both ends and saying I have to get from here to here. How can I do that? So this leads to this. This is equivalent to this. So I need to close in the middle. Well, what I do know is that negative b in the set of integers is just negative 1 times the number itself. So if b is nk2, then negative b should just be negative nk2. I already know a is nk1. So what I'm going to do is I'm just going to start off with a plus negative b, and I'm going to rewrite these, and what I have for the definition of a and b is just nk1 plus negative nk2. Now the goal is to write this as n times some integer. So what I'm going to do here is say, oh look, there's an n in both of those, so let's factor that out. And I get n times k1 minus k2, or plus negative k2. But now I have n times k1 minus k2. Notice, however, that this is an integer and this is an integer. Since the integers are closed under differences, this k1 minus k2 has to be an integer. So I'm just going to let k3 equal k1 minus k2. Then I get exactly what I wanted. A plus negative b is n times some integer, k3. So therefore, we get that a plus negative b is again in nz. So therefore, nz is indeed a subgroup of z under addition. Thank you for joining me today. I hope you found this video helpful. If you did, make sure to like the video and subscribe to the channel.